Our sun, the star of our solar system, is a dynamic celestial body constantly in motion and full of energy. It sometimes unleashes incredible bursts of energy known as solar flares, which are sudden and intense variations in brightness. Imagine colossal explosions on the sun's surface with energy equivalent to millions of nuclear bombs. These flares release vast amounts of radiation into space, affecting everything in their path. These events have profound significance for Earth and our technological civilization, impacting communication systems, navigation, and even power grids. Solar flares are among the most powerful explosive events in our solar system, showcasing the immense power of our sun. When a flare erupts, it releases energy equivalent to millions of hydrogen bombs, sending shockwaves through space. This energy travels across the electromagnetic spectrum, reaching Earth in minutes, and can disrupt satellite operations and communication networks. Understanding solar flares is crucial for protecting astronauts, satellites, and power grids from these potentially harmful effects. NASA dedicates significant resources to studying these solar outbursts, using advanced spacecraft and instruments to monitor the sun's activity. By studying our sun's flares, we learn more about how stars work and interact with planetary systems, gaining insights into the fundamental processes of the universe. Our sun is just one of billions of stars in the Milky Way galaxy, many of which experience similar flaring activity, indicating that solar flares are a common phenomenon in the universe. The quest to understand solar flares is part of our cosmic journey to comprehend the universe, helping us to unlock the mysteries of stellar behavior. These events remind us that we live in a dynamic cosmic environment where the sun's activity can have far-reaching effects. As our reliance on technology grows, so does our vulnerability to solar storms, making it essential to develop strategies to mitigate their impact. NASA's mission to unravel the mysteries of solar flares is more important than ever, as we seek to protect our technological infrastructure and ensure the safety of space missions. It's about safeguarding our future by understanding the star that makes our existence possible, and preparing for the challenges posed by its activity. Solar flares are a natural part of the sun's behavior, a consequence of its powerful magnetic fields and the complex interactions within its plasma. These magnetic fields twist and snap, releasing energy in the form of solar flares, which can have significant effects on our planet and beyond. As we continue to explore space and expand our presence beyond Earth, understanding solar flares will be crucial for the safety and success of future missions. The sun's influence extends throughout the solar system, and by studying solar flares, we gain a deeper appreciation of the interconnected nature of our cosmic environment. This research is a global effort, with scientists from around the world collaborating to unlock the secrets of our sun and protect our technological society. Solar flares are a testament to the vibrant and dynamic nature of our sun, reminding us of the powerful forces at play in our universe. As we bask in the sunlight that sustains life on Earth, we must also be mindful of the sun's more volatile aspects and prepare for the challenges they present. What triggers these immense explosions on the sun? These powerful bursts of energy, known as solar flares, are among the most dramatic events in our solar system. The answer lies in its magnetic fields. These invisible lines of force are constantly shifting and changing, creating a dynamic and sometimes volatile environment. The sun is a giant ball of superheated gas, mostly hydrogen and helium, in a state called plasma. This plasma is not just hot, it's incredibly energetic, with temperatures reaching millions of degrees. This plasma generates immense magnetic fields, which can twist and tangle. These magnetic fields are like rubber bands, storing energy as they become more twisted and stressed. Solar flares occur when these tangled magnetic field lines suddenly reconfigure. This sudden change releases a tremendous amount of energy in a very short time. This process, called magnetic reconnection, releases stored magnetic energy. It's like snapping a stretched rubber band, releasing all the built-up tension in an instant. The released energy heats the surrounding plasma and accelerates particles. These particles can then travel at nearly the speed of light, creating intense radiation. The regions on the sun where flares are most likely to occur are called active regions. These areas are hotbeds of magnetic activity, often marked by sunspots. These areas have strong, complex magnetic fields, often associated with sunspots. Sunspots are cooler, darker areas on the sun's surface where magnetic fields are particularly intense. Understanding magnetic reconnection is key to predicting solar flares. By studying how and when these magnetic fields will snap, scientists hope to forecast these powerful events. Scientists use sophisticated models and observations to study these magnetic structures. They employ advanced technologies such as space telescopes and solar probes to gather data. They hope to identify signs that a region is primed for a major eruption. By recognizing these signs, we can better prepare for the impacts of solar flares on Earth. It's like predicting an earthquake by studying stresses in Earth's crust, but on a stellar scale. Just as seismologists look for patterns in the Earth's movements, solar scientists look for patterns in the sun's magnetic fields. When a solar flare erupts, it unleashes a torrent of radiation. X-rays and extreme ultraviolet radiation reach Earth in about 8 minutes. These affect the ionosphere, crucial for radio communications. Intense X-rays increase ionization in the ionosphere's D region, absorbing HF radio waves. This leads to radio blackouts, affecting HF communications on the sunlit side of Earth. Pilots, mariners, and emergency responders rely on HF radio, which can be disrupted. The severity of the blackout depends on the solar flare's intensity. NASA and NOAA monitor the sun for flares to provide warnings about potential blackouts. Understanding solar X-rays' interaction with the ionosphere is key to space weather forecasting. Events on the sun can have immediate consequences for our technologically dependent society. Strong solar flares, especially with coronal mass ejections, CMEs, can disrupt Earth. CMEs can induce geomagnetically induced currents, GICs, in power lines, pipelines, and railways. Power grids are vulnerable to GICs, which can overload transformers and cause outages. Satellites are at risk from increased radiation, which can damage electronics. The atmosphere expands with solar activity, affecting satellite orbits. Understanding and predicting solar flares and CMEs is critical for planetary defense. NASA's research helps develop better forecasting models and early warnings. Solar flares are connected to the auroras, nature's breathtaking light show. CMEs and solar wind particles energize the auroras, creating shimmering curtains of light. When these particles reach Earth, they collide with atmospheric atoms, emitting light. The aurora's colors depend on the gas excited in the altitude. Strong solar storms intensify auroras, visible further from the poles. The auroras remind us of the Sun-Earth connection and the forces at play in space. NASA studies auroras to understand energy transfer from the Sun to Earth. They are a natural laboratory for studying plasma physics and magnetosphere dynamics. NASA's Solar Dynamics Observatory, SDO, is crucial for understanding solar flares. Launched in 2010, SDO studies solar activity and space weather. It orbits Earth, providing continuous observation of the Sun. SDO's instruments capture images of the Sun's atmosphere in multiple wavelengths. The helioseismic and magnetic imager maps the Sun's magnetic fields. SDO's data revolutionizes our understanding of the Sun and improves space weather forecasts. It's a cornerstone of NASA's Living with a Star program. SOHO and Parker Solar Probe offer different perspectives on the Sun. SOHO, a joint NASA-ESA mission, has been a solar science workhorse since 1995. It observes the Sun's corona and CMEs, providing vital data for predicting solar storms. Parker Solar Probe, launched in 2018, flies through the Sun's outer atmosphere. It measures solar plasma, magnetic fields, and energetic particles. Parker Solar Probe's data transforms our understanding of solar physics. These missions improve our ability to predict space weather events affecting Earth. Solar flares are classified by their X-ray brightness, which is a measure of the energy they release. The system categorizes flares into 5 distinct classes: A, B, C, M, and X, each representing a different level of intensity. Each class represents a 10-fold increase in energy output, meaning an M-class flare is 10 times more powerful than a C-class flare. A-class and B-class flares are the least intense and are quite common. They generally have little to no effect on Earth's environment. C-class flares, while still relatively minor, can cause some radio disturbances, particularly affecting high-frequency communication systems. M-class flares are more significant. They can cause brief radio blackouts and minor radiation storms, which can affect satellites and astronauts in space. X-class flares are the most powerful and are considered major events. They can trigger planet-wide radio blackouts and pose serious risks to space missions. If an X-class flare is associated with a coronal mass ejection, CME, it can lead to severe geomagnetic storms, which can disrupt power grids and navigation systems on Earth. Flares are further ranked with a number indicating their power within their class. For example, an X2 flare is twice as powerful as an X1 flare. The largest flare ever measured was around X28 in 2003, which caused significant disruptions in communication and navigation systems. Understanding the flare classification system is crucial for scientists to predict their potential impacts on Earth and to mitigate their effects. This classification system aids in space weather forecasting, allowing for better preparedness and response strategies. It ensures that we are ready for the sun's powerful outbursts, protecting our technology and infrastructure from potential damage. NASA's quest to understand solar flares is ongoing. The sun's outbursts drive the space environment of our solar system. NASA uses spacecraft, instrumentation, and modeling to study solar activity. This knowledge is vital for our modern life and future space aspirations. Missions like SDO, Parker Solar Probe, and Solar Orbiter provide constant data. The goal is to improve space weather prediction and protective measures. International collaboration enhances our understanding of solar activity. NASA's efforts ensure we are prepared for the sun's fiery temper,